Hello. I think I'm ready. Zoom still is acting strange. Do you hear me? Do you see the desktop?
Yes,
Do you see the desktop? Can you hear me? Does everything seem okay?
I can see the desktop and
Not
I can
hearing
hear you.
anything.
Hello?
We can hear you.
Are you there, Professor?
Oh, okay. Saw something in the chat. Okay. I don't know if I can hear you. I'm not hearing anything, but okay. The desktop, does the desktop look okay? All right. Okay, well, want to pick up where we were? We were talking about this picture here. I'm going to just go ahead and download it and kind of pick up talking about this picture and use it to describe what we're really doing is these two chapters in the book. So there's this chapter here and this chapter here. Notice that the titles of the chapter are kind of important in one sense. This chapter is called The Abstraction, and the next chapter is called Mechanism. And that's going to be a theme. It's actually a theme throughout all of computer science, and it's a theme through this book. The abstraction is something you want to do. It's what you want. The abstraction we want is process. We want that abstraction, but this is an abstraction is what you want. A mechanism is how you do it. Okay. Now, another pair of words that represent this would be the interface and the implementation. Okay. Now, in operating systems, it's more likely to refer to the abstraction and the mechanism, but it's pretty much the same dichotomy that's used in programming to talk about an interface, which is what you want, and then it's a description of what you want, and then an implementation which describes the actual how you do it. Like in Java, you have abstract classes and interfaces, which are abstractions. They're interfaces. They describe what you want done. An abstract class or an interface says, this is what I want, but then somebody has to provide an implementation of them. And here they refer to that as the mechanism. Okay. The mechanism, the how we create processes is called limited direct execution. Yesterday, we talked about another mechanism that's not in the book, and that was cooperative multitasking. Cooperative multitasking is another mechanism for creating processes, but it's not a very good one. So, because it really doesn't create a very good process abstraction, it creates a very weak process abstraction. Because remember, with the cooperative multitasking, you have these two processes. They're running independent of each other, kind of. If one process chooses not to call yield, the other process never sees the CPU again. Okay, so the two processes are sharing the CPU. They, in a sense, they seem to be independent of each other, but the process abstraction is real weak because one process can take over. We want a really strong process abstraction that really says processes don't know about each other. No one process can do anything to harm another process. That's one of the goals in this process abstraction. Yeah, he describes it in words. There's no place where it's not like writing an abstract base class where you just lay out an abstraction rigorously. Here, the abstraction's described in words, but what we want is that essentially a program running in memory to feel like it owns the CPU. So roughly, it's this process kind of feels like it owns the CPU. Simultaneously, this process feels like it owns the CPU. Neither process knows about the existence of the other process. Neither process can do anything to harm or influence the other processes. They're isolated from each other. Okay, that's the abstraction we want. Okay, now the cooperative multitasking is very weak because if one process stops cooperating, it takes over the CPU. So it just can hog the CPU for as long as it wants without calling yield. So that's a weak abstraction, but it is a mechanism. It's a mechanism for providing this process abstraction. In the textbook, we'll see this again. You go to the table of contents of the textbook. Where's, oh. For example, when we get to here to virtual memory, see, there's the next abstraction we'll want. The abstraction is address spaces. So that'll be chapter 13, that'll be the virtual memory abstraction. And then the mechanism will be address translation. That'll be one way to create these virtual address spaces. It won't be the only way, but it's the way that modern computers do it. Okay, so and then this mechanism actually breaks down into several sub-mechanisms, segmentation and page tables. So we'll see that we have an abstraction and a mechanism. Over here we have an abstraction and a mechanism. He didn't put those words in the table of contents. I think he actually should have, because it's actually one of the themes of the book is abstract. It's actually a theme in all of operating systems and through most of computer programming too. You program by first defining what you want. What is your abstraction? Then after you figured out what your abstraction should be, then you figure out how to do it. If you look in the world of programmers and you look at who makes a lot more money and who makes less money, who's the experienced programmers, who's the lower level programmers, it boils down to basically the high level programmers are the ones who decide what should be done. They design things. They design the abstractions. And then lower level programmers implement the abstractions. And that's pretty common, especially in large organizations. And in small projects, it's usually one or two people doing both. They're designing it and writing it. But in a large organization, you almost always have people divided by levels. The designers are designing abstractions. They decide what should be done. How should the software communicate with itself? And then somebody else does the mechanisms, the implementations. So it's a real common theme in computer science. Okay, separating abstraction from mechanism, or more common way to say it is separating interface from implementation. Okay, operating system people like to use the words abstraction and mechanism, but most programming languages and most computer science people actually use the words interfaces and implementation. So for example, in Java, you have the word interface. You have classes can be either concrete classes, abstract classes, or interfaces. So the word interface means literally this idea of an abstraction. Okay. All right. So we want to right now talk about the this mechanism is the mechanism we're really interested in. Okay. That's the harder part. So there's what we're trying to do, create this abstraction, and roughly the abstraction can be described kind of easily. Processes shouldn't know about each other and shouldn't influence each other. Processes should feel like they own the CPU, and eventually we'll see that processes should feel that they own all of memory. You know, this process should actually think that that's all the memory that there is in the computer. It shouldn't even know that there's this other memory out there that it doesn't see. It should just think this process should have the impression that it controls all of memory and it totally controls the CPU. And it should not know that there's any other processes. What's sometimes referred to as isolation. Processes shouldn't be able to, they should know about each other, and then they shouldn't be able to influence each other. And then later in the course, we'll learn how to break that. Because here's a problem. If this process doesn't know anything about this process, and this process can't influence that process in any way, how in the world does Chrome work? Because my browser, this guy, is really a whole slew of processes. You can see them over here. This browser is a slew of processes. Right now, it's about 20 of them. But this is all one program. If these processes are completely isolated from each other, don't know that each other exists, and can't influence each other, then I can't have this kind of thing. So what we then, after we build the abstraction process, we learn how to essentially break through it. We then learn what's called interprocess communication, IPC. See, if IPC is usually quite often here, interprocess communication, IPC, okay? So interprocess communication is then how do you break down this barrier between processes? And essentially and this is actually real important because the textbook implies that the whole goal is to create this barrier between these two processes. And the textbook actually doesn't spend a lot of time talking about interprocess communication. But from the point of view of a real programmer, the whole point is after you've created this barrier, you want to break through it so that you can write programs like Chrome. The fundamental way you break this barrier is that if this process wants to cooperate with this process, if it wants to communicate with that process, it has to do it through the operating system. So essentially, the operating system acts as a middleman. This process in no way can communicate with that process. It just doesn't work that way. Instead, what happens is that process can tell the operating system, please tell this other process something for me. And then this process gets a message from the operating system from that process. And then that process can reply to that process by sending another message through the operating system. All the communication between the processes, all the cooperation between the processes is done through the operating system, which is a little bit inefficient, but it's a price we pay for this process abstraction. So even over here, I mentioned that Chrome wasn't originally designed this way, and Firefox wasn't originally designed this way because you pay a certain penalty in doing it this way. But over time, they realized that they had such a problem with one tab screwing up and all the tabs dying that they finally decided that they needed this hard isolation of one tab here being isolated from another tab here, but then the tabs can work together, but through this extra layer of having to communicate through the operating system. So they ended up with this design because they realized the hard way that that was the only way they could keep these tabs from blowing up each other. That was the only way to keep these tabs from, if one tab does something, usually it was the JavaScript. If the JavaScript in this tab goes bonkers, that doesn't necessarily affect this tab here or this tab here. The only way they tried a bunch of ways of doing that, and it finally came down to put one tab in a process and put another tab in a process and let the operating system be the barrier between them. That's really safe, but you do have to, it's harder to program, and it does make things a little bit more inefficient. Chrome is now a notorious memory hog. It takes lots of memory to run Chrome, and I think that's part of the reason is because it's kind of designed in this cumbersome way, but that cumbersome way is effective. Now, you no longer have one tab blowing up and blowing up all the other tabs, which was a common problem for years with Firefox and Chrome both. Okay, so once you set up this abstraction, the next step is to find a way to get around the abstraction, but you really don't break the abstraction. What you do is you just provide more mechanisms. You actually provide new mechanisms that are communication mechanisms. You actually start creating new interfaces where this guy can communicate with this guy through the operating system. But the operating system acts as the middleman. This guy will never know that this process doesn't see this process as memory. This process can't do anything to the CPU that affects that process, but this process can send a message to the operating system asking the operating system to send a message to that process. And that's very effective. It ends up being one of the cornerstones of modern programming for operating. I mean, you can see it's used all over the place in Chrome, and there's quite a few other programs that use that idea too. Okay, so it's become a very important design feature. It's not an easy design feature. The inter-process communication mechanisms are all hard to program. They're not easy to program. Okay, yeah, and here's a list of them. Like here's a list of inter-process communication mechanisms: sockets, messages, sockets, pipes, shared memory, message passing. So these are all libraries that exist in. There's a whole bunch of ways for one process to help to communicate with another process. And what's happened is over the years, some of these have been fallen out of favor, and some of these have been invented, and then new ones get invented. So we ended up with a whole bunch of these. We end up with a whole bunch of these inter-process communication mechanisms. Some of these are in both Windows and Linux. Some are only in Windows. Some are only in Linux. Most, I think, are in both. Most of these mechanisms for interprocess communication, I think, exist both in Windows and Linux now. Okay, so the starting point is the abstraction, what we want. We want processes to be isolated from each other. How are you going to do that? Well, there's more than one way to do it, but first you want to describe what you want to do. You want, he calls it here the crux of the problem. Yeah, he calls it something, the crux of the problem. What do you want to do? You want to run more than one program at a time. You want to be able to run Word the same time you're running Chrome, at the same time you're running PowerPoint, at the same time you're listening to music, the same time you have a chat program going. You want to run all those things simultaneously, but you also don't want one of them crashing to crash everything else. Okay, so that's what we want: isolated processes that run simultaneously on one CPU. Remember, one mechanism for this would be, oh, if you want to run 10 processes, go out and buy 10 CPUs. Okay, that would be a mechanism, but it's never been done because you can't go out and CPUs are very expensive. Even today, it's hard to get more than 8 CPUs. My computer actually, if you look on my machine, it seems to say that it has 12 CPUs, but it doesn't. It only has 6 CPUs. Not all of these CPUs are actually physical CPUs. Later, there's something called hyperthreading. These are actually virtual CPUs. Every 2 of these makes one physical CPU. So this computer actually only has 6 physical CPUs. And I think you can get 8 physical CPUs, which look like 16s. The Windows will show it as 16 CPUs here. The CPUs are expensive. So you don't, but I'm running, right now, if I'm running about 100 processes. So one mechanism would say, oh, you want to run multiple processes, get a CPU for every process. But that's a really lousy implementation of the abstraction. That would be a mechanism to give us this abstraction, but it would be a very bad one. One CPU for this process, one CPU for that process, one CPU for every other process. Okay, so we need a mechanism that shares a CPU. Now, if I have multiple CPUs, then there's just less sharing going on. If I have 4 CPUs and I'm running 4 processes, I can just literally put one process on each CPU. But if I have 4 CPUs and I'm running 10 processes, then I have to put multiple processes on each CPU. Okay, so and on a modern computer, you pretty much, if you check your own machine, you'll see that you probably have upwards of 100 processes running at any given time. Your machines are busy. They're doing a lot of stuff. A lot of these processes are weird things running in the background. Update processes for different programs, programs that are just listening to the internet to see if you're getting messages coming in. The operating system itself is monitoring various devices on the computer. Over time, you could actually, if you really like operating systems and really like to know about Windows or Linux, you can eventually learn what most of these do. Your machine and my machine, most of what's running over here would be the same. Most of this is stuff that's got to do with Windows. Okay, so see, all this is Windows. All that's Windows. This is what I'm running. So this is the stuff, see, it's under, I'm logged in as Classroom. So this is the stuff I'm running. And then this stuff down here, System, is back to Windows. So you would probably have exactly those processes running on your computer because that's part of the operating system. And you would probably have most of these running on your computer too, okay? Which are mostly Windows, okay? So Windows itself is just got a ton of processes. And then I get weird things. See, like that process there, okay, I'm running a Lenovo laptop. So God knows what Lenovo's doing on my machine, but they're running a process there. And like if you got a Dell computer or an HP computer, you probably have some processes running that are put there by the manufacturer, and you kind of hope that they're not doing anything like spying on you. And it's been discovered quite often that they are spying on you. It's really a mess, but these processes are running as part of the operating system, but they're not part of Windows. They're put there by the manufacturer of your computer. So if you have a Lenovo computer, you probably have processes like those. If you have a HP computer, you probably have you have some other thing from HP that's running on your computer. But those are running probably as part of the operating system. But most of this is the Windows operating system. And you can look up what these are. You can actually, a lot of these, you can Google them by name. They're well enough known that you can Google these things by name and find out what they do. When it says SRV, it's something called a service. That's Microsoft's virus scanner, if I remember right. That I think that's the virus scanner there, this one here. Okay, so you can learn what a lot of these are. But your machine's going to be running upwards of 100 processes all the time, and a lot of them are just the operating system. A lot. You can see how many of them are the operating system. Majority of what's running on my computer right now are processes put there by the operating system. And then then Chrome is a whole bunch of processes. I only have a few tabs open. Okay. And then there's other things that I happen to be running. Okay. Like Dropbox runs in the background. I use Dropbox once a week or so, but it's got 3 processes running in the background all the time. And I hardly even use it, but it's running 3 processes all the time. And I'm not sure why there's 3 of them, but Dropbox by itself is 3 processes. They communicate with each other. I'm sure those 3 processes they're designed just like Chrome is. The 3 of them somehow work together to be Dropbox on my machine. Okay, so I'm sure this is designed the same way Chrome is, that they're somehow working together to be Dropbox, but they're designed to be 3 separate processes. Then OneDrive from Microsoft, again, that's one process. Okay, and you can see like here, there's a whole bunch of processes with the same name. I don't know what that is. Like, I don't know if those are running independent of each other or if they're like Chrome. Like, I know the Chrome processes are all working together. Those I know are working together to be this. Okay. The Dropboxes are probably working together to be Dropbox. But these, they might be working together or they might be working independently. Like if I start up 2 notepads, remember, if I start up 2 notepads, that's an example of processes that are not communicating with each other. So there's a notepad process that I just created. Where is it? Are these in alphabetical order? Okay, there's that notepad process. Now I can create another notepad. Okay. Now there's an example of 2 processes. They have the same name, but those are not cooperating with each other. Notepad doesn't have a clue how to communicate between notepads. So those are not cooperating or communicating processes. Okay. I know the Chromes are communicating with each other. Try to give it. I know that these are communicating with each other because they're building one GUI all together. Okay, I'm guessing that the Dropboxes were communicating with each other. I'm guessing that where are they? I'm guessing that these 3 are working together. Okay, and I know for sure that the notepads aren't. They do not have, there's no interprocess communication between those notepads. Okay. All right. So the mechanism, the abstraction is processes that initially, without extra effort, processes that are isolated from each other, completely isolated processes. The mechanism is this thing called limited direct execution. Okay, let's go back to the picture that built that mechanism. So here's the picture. The mechanism, and this is real important, the mechanism needs hardware support. You cannot write code to do this. You cannot get the abstraction of processes without cooperation from the hardware. The CPU has to have been designed to do this for you. And that's why I've mentioned here today, operating systems can't exist without the architecture class, because you can't design an operating system without a properly designed CPU. If you buy a cheap CPU for pennies that's meant to be stuck inside of a toy, it's not going to be able to run an operating system because it won't be worth their money to put these features in that toy CPU. So you need a certain level of sophistication in the CPU before it can run an operating system. I don't know what the cheapest CPU is that'll run an operating system right now. My guess is probably for $1 or $2. Yeah, the Raspberry Pi can run an operating system. Okay, Raspberry Pi is a pretty powerful CPU. I don't know if an Arduino, for example, I don't know if the Arduino, I've never looked into the architecture of the Arduino. I have a feeling it might not be powerful enough to run an operating system. Anybody know? Does anybody know if an Arduino runs an operating system? The Raspberry Pi, you can boot Linux on it. And Raspberry Pis can be bought, yeah, for dollars. Does anybody know if an Arduino can boot an operating system? I don't remember seeing references to that. Yeah, I don't know if an Arduino is powerful enough. Yeah, Arduino's a pretty little thing. They're really small computers, and I don't know if they're real popular for projects. I don't know if they can run an operating system. Definitely the Raspberry Pi can. The Raspberry Pi can run Linux. It can run Windows. Microsoft has a version of Windows that runs on the Raspberry Pi. You can't buy it, but it exists. Okay. All right. So now, what is it you need in the CPU? The main thing you need is this mode bit that switches the CPU between kernel mode and user mode. Okay, that's the core idea. And then you need interrupts so that you can have an interrupt come in every 50 milliseconds and tell the CPU to do two things: switch from user mode, so it's in user mode when it's running a process. You tell it to switch from user mode to kernel mode, and you tell it to go jump into the kernel to do the next scheduling process of deciding what process to do next. So this process has no say in the matter. If this process is running, he doesn't yield the CPU is stolen from him. When the interrupt occurs, the hardware design of the CPU, when it sees that interrupt, it does two things: switches from user mode to kernel mode, and then jumps the program counter into here. Oh, and then when you're here in user mode, the point of user mode is this process can't be malicious and say, I'm going to go turn off that interrupt, or I'm going to set that mode bit to 1 and take over the CPU. When you're in user mode, a large chunk of the CPU is disabled. Okay, so the CPU is not a full, it's what we call a virtual CPU. So I drew it in the picture as a virtual CPU. When you're in user mode, like if I wanted to, I could, to make the picture maybe, think of it this way. Let's say that user mode is in red, okay? So user mode is a 1 in red, okay? So when you're in user mode, you're running the virtual CPU, okay? So think of it that way. When you're in user mode, you're running the virtual CPU. When the mode bit is 1, you're a virtual CPU. When the mode bit is 1, the CPU has several features are disabled. So for example, one feature that's disabled is the ability to switch back to kernel mode. When you're in user mode, the only thing that'll put you back in kernel mode is one of these interrupts. It takes an interrupt to put you from user mode into kernel mode. So that's important. This guy can't do anything to switch the CPU into kernel mode so that he could take over the CPU. And when he's in user mode, he also cannot access that interrupt. He can't access that timer, okay? Also, when he's in user mode, he can't access this memory down here. Now that's the next part of the book. How does that happen? That's this thing that we'll talk about in the next part of the book, the memory management unit. But when this guy's running, when this guy's in user mode, when this mode bit is 1, and the virtual CPU is run, essentially we think of it as this CPU has become this virtual CPU. At that point, this guy can't see anything but that much memory. He can't see that memory down there, and importantly, he can't see the operating system memory, so he can't go muck around in the operating system and make changes to the operating system. This process only sees that memory. This process can do anything it wants to that memory. You can write any data you want in there. You can read anything you want in there. This process's memory. It has total control over it, but it doesn't see anything out here, doesn't see anything down there. So we think of that as the virtual CPU. The mode bit is 1. The interrupt switches you to the mode bit 0. The CPU now is a full-fledged CPU, okay, physical CPU you might call it, not a virtual CPU. But then also, when that happens, the program counter is forced by the hardware into this chunk of memory, which means you're now running operating system code. Now, think this code, he can't change it. Think about the boot process. This code was put there when you boot the computer. Once you've put this code in there in the boot process, no other process can actually update that memory, because then there's only, so the boot process puts the operating system in memory. After the boot process is done, the first process is created, and then another process created. But at that point, you're switching to user mode. So all these things run in user mode. So the only thing that can change what's up here, the only thing that can update that code, manipulate that code, is the operating system itself or the boot process. The boot process puts that code there. And then if the operating system wanted to, it could update that code while it's running, but no other process can do that. Now, one lesson of that is that if you want to attack a computer, one point in time to attack a computer is during the boot process, because the boot process is when the kernel is being written into memory. If you can influence the boot process, you can modify this kernel. So that's one way to attack a computer, because once the boot process is done and this mechanism of user mode, kernel mode kicks in, it becomes way harder to attack the kernel, because it's hard to attack the kernel from user mode, but there's lots of ways that people have invented, lots of ways to attack the kernel from user mode. Oh, here's one way to think about it. We decide we want this abstraction. We want the abstraction of a process. We have this mechanism. The mechanism is not foolproof. This abstraction is not foolproof. Hackers find all kinds of ways of breaking that abstraction. Okay, so that's what hacking is about, is this abstraction is not foolproof. There are ways, if you really work hard enough, for this process to look inside that process. That's what attacking computers is all about. Finding clever ways that Intel didn't think about, and Microsoft didn't think about, and Linux didn't think about, finding clever ways for this process to see inside of that process. And even if you're in user mode, to break the abstraction, to break this abstraction, it can be done, and it's a cat and mouse game. It's happening all the time. It just goes on and on and on. Every time Intel and Microsoft patch up another hole in that abstraction, somebody finds another hole in the abstraction. The abstraction is very complicated. The mechanism that implements it's very complicated, and there's bugs in it. And attackers find holes in this abstraction. In theory, the abstraction is concrete and works fine, and that's what the book talks about. The abstraction in its theoretical, it works great. Yeah, in theory, it works great. In practice, it's got all kinds. In practice, they find holes in it almost monthly. Okay, but the holes are not easy to exploit. They can take. It can take years to find these holes. It takes a lot of effort. But when people find them, if they keep them secret and use them, they can use them to attack computers. Okay, so the abstraction is not bulletproof. It's not foolproof. There are holes in the abstraction. Okay, all right. So the abstraction again is virtual CPU, meaning user mode. So virtual CPU means user mode. When you're in user mode, your process is in user mode. The CPU is intentionally crippled slightly so that you can't supposedly do malicious things. You can't supposedly see inside that process or see inside the operating system. again, and you can, if you really know what you're doing, you can break the abstraction, but it's not easy. Okay. All right. So the virtual CPU, this mode bit and the interrupt, essentially they create the abstraction. All right. Now, there's a level of detail that we haven't talked about. The actual switching from this process to this process. Let's talk about the details of what it means to, it's called a context switch. When this interrupt, suppose you're running this process here, okay, and this interrupt fires because it's this guy's turn, his guy's turn on the CPU is up. So it's time for the operating system to pick somebody else to use the CPU. Exactly how does this, what's called context switch, how do you switch from this context to this other context? Okay, so that's where this process control block comes in. Okay? The CPU has what we call state. At any given time, there's a number in this register, a number in that register, and a number in every one of the registers. We call that the state of the CPU. The state is used as a word meaning what are your values? What state are you in? The word state is overlaid. It's not what state are you in? Are you in Indiana or in Illinois? This is the state as in what are the values of all your it's what are the values of all your registers? Okay. When this interrupt happens, the CPU what actually happens when this interrupt happens? Probably the CPU. Remember, the CPU is in a fetch, decode, execute cycle. There's a program counter. The program counter is a value, points to a memory location. You grab what's in the memory location, put it in the instruction register, decode what's in the instruction register, execute the instruction. The interrupt probably happens in the middle of that. So what the CPU does is when it gets to the top of this loop, that's when it acknowledges the interrupt. If the interrupt comes in the middle of decode, the CPU kind of just says, "Oh, okay, we're going to wait. We're not going to interrupt the middle of a decode step." So the CPU finishes the decode step, finishes the execute step, goes up here, and actually you could put a little line in here that says check for interrupts. If you go back to the architecture book and you look at these loops real carefully, you'll see that usually at the beginning of this little loop is check for interrupt. Okay, so you notice that there's an interrupt. That means that you've just finished an instruction over here. Okay, so what you can do is you could just pause. You can essentially at that point pause this process. The way you do it is that you take all these register values and you copy them into the process control block. So if at the top of this loop you see, yes, there's an interrupt, what that does is it remember, the interrupt puts a value in the program counter that sends you into the operating system. When you get into the operating system, the first thing the operating system does is copy all this state information from the CPU into the process control block. That essentially freezes this process. Essentially, you keep a record of exactly where that process was. What program counter was it interrupted at? What was in all its registers? So all that state information is copied from the CPU into the process control block. This is actually another place where you need help from the CPU. There is the ability to copy all the registers of the CPU into a process. Now, the process control block is actually a data structure in memory. It's a data structure living up here somewhere in the operating system's memory. The operating system is this process control block here, this process control block here are really data structures living up here. The CPU actually has an instruction that makes this, that helps, that it will take all the registers and copy them. The reason you need a special CPU's instruction is if you were to try to write code that would copy all these registers, the code would manipulate those registers and overwrite what's in them. You need something that just says, immediately copy all these registers exactly the way they are into memory. So you can't write your own code to do that, because if you wrote your own code, you'd be, the only way to run code is to run code that manipulates these registers. So the first thing the operating system does is it executes a special CPU instruction that essentially copies all the data in the registers directly into the process control block. Okay, that freezes this process in place. So this process essentially is frozen. The program counter where you were when the interrupt happened and all its registers are in the process control block. Okay. Then the CPU starts executing operating system code. At some point, the operating system decides, oh, I want to run this CPU, this process. Well, this process's state is in its process control block. So when the operating system says it's time to go and start, I picked who I want to run this process here. The operating system says to the CPU, take that process control block, load it into the CPU. Part of the process control block is the program counter. When that program counter is loaded into the CPU, you will immediately jump into that process. And loading the process control block into the CPU also puts you back in user mode. So the kernel's running in kernel mode. The last thing the kernel does is tell the CPU, load the process control block of this process into the CPU, and which will restore the program counter to whatever was down here. So that jumps the CPU into here, but it also puts the CPU back in user mode, so that when the CPU does end up back in here with this state back into the CPU, this process picks up without even knowing got interrupted. This process will pick up back in user mode without even having known that it was interrupted. Okay, then this process runs until an interrupt happens over here. When that interrupt happens over here, again, the mode bits switch to kernel mode. The program counter is forced into the operating system. The first thing the operating system does is executes this special CPU instruction that loads everything into the CPU into that process control block. That freezes this process in this process control block. And then the operating system says, okay, now I need to decide who I want to run next. That's the next chapter in the book, scheduling. How do you decide who to run next? And one on the course website, there's a reading assignment to start reading the chapter on scheduling. That's a decision process. That's not a mechanism. That's a decision process. That says, the operating system just wants to decide who to run next, and it needs to worry about fairness and all kinds of things. So there's a whole bunch of things that have come up about what's the best way to choose the next process to run. But right now we're talking about the mechanism. What literally do you do to go from this process to this process? Without saying how we decide who to run next. For example, it might be that when this interrupt occurs and this process is interrupted, the kernel might decide he's the most important process on this computer, go right back to him. So there may not even be a context switch. When this process is interrupted, the operating system might say, well, just take this process control block and put it right back into the CPU and keep running that process. That process may have the highest priority. One of the things we'll talk about are priorities. Okay, so it might even be that this interrupt happens and this process the operating system says, stick with this process. Or it might be the operating system decides, no, there's some other process that's more important. So we'll switch to this other process by loading its process control block into the CPU. Okay. All right. So the mechanism is this combination of interrupts, mode bit, the ability of the CPU to force the program counter value into the force of value into the program counter to direction into the operating system, the ability of a CPU to take the state of the CPU and store it in memory in a process control block, and the ability of the CPU to load state from a process control block in memory back into the CPU. So there's a lot of hardware support, and eventually we'll see there's also this memory management unit, which is the thing that keeps this program counter from jumping out of this region and keeps these registers in this region of memory here. So we're not talking about that yet, but eventually we'll see that's more hardware support. Okay, so we need interrupts, user mode, kernel mode. We need interrupt vector. Somewhere in the CPU, there's a number stored in the CPU that is the number that you put in the program counter when that interrupt happens. That number is physically stored in the CPU. It's called the interrupt vector. You need that vector in the CPU so that when this interrupt happens, a very specific address gets punched into the program counter, so you go into the operating system. Okay, so you need that in the operating system. Then you need this ability for the CPU to be able to store its state in the process control block, and for the CPU to be able to load its state from a process control block. All those things are part of the CPU. Okay. Obviously, a Pentium CPU has all that ability in it, and it didn't. The original Pentium, I'm sorry, the original Intel CPUs that didn't. If you go back to the days of DOS and the early Apple operating systems and the early Windows operating systems, they were cooperatively multitasked because all this hardware wasn't in the CPU. The CPU did not have all this stuff in it back in the 80s, actually even in the early 90s. The Intel CPUs did not yet have all these features. It was, I forget exactly what year it was when Intel finally was able to build a CPU that could run an operating system. Okay, Intel made tons of money building CPUs. They couldn't run an operating system for a while. They grew to be a giant company building CPUs that weren't actually quite able to run an operating system. But they did the research, they did the design. Their goal was to build. It took them a while to get to where their CPUs could run a real operating system. And Microsoft didn't write a real operating system until it wrote Windows NT. DOS wasn't a real operating system. It was cooperative multitask. Windows 95 wasn't a real operating system. It wasn't until they got to this thing called Windows NT that they finally that Microsoft wrote a real operating system using the features of the Intel CPU that supported a real operating system. And Apple went through the same phase. At some point, Apple switched from being a baby multitask, a cooperatively multitask operating system, to being a real operating system. That's when they got OS 10. Before OS 10, it was not a real operating system. It was a cooperatively multitask operating system. Okay, so OS 10, which is still the current operating system, it's gone through many variations, but that's when Apple started becoming a real operating system. If you look at your cell phones, for a while, cell phones weren't running real operating systems. Smartphones didn't. There was a time when smartphones weren't real operating systems. They were these cooperatively multitasked operating systems. The operating systems you run on your cell phones now are real operating systems. The modern cell phone, a modern smartphone is running essentially a baby version of Linux. But it's running it's running an operating system like this. It's running an operating system that's based between user mode and kernel mode. Okay, so your cell phone, your smartphone does do this right now, but it didn't a few years ago. I don't know. I don't know when they switched from essentially being a cooperative multitask baby operating system to a real operating system in this theoretical sense. Okay, it wasn't recently. It was some time ago. But at some point, I know they weren't real operating systems, and the point was, it took them a while to design a CPU that was small enough and low power enough to fit in a cell phone and could have all these features. Putting all these features in a CPU was not easy, and to make it run on a battery. So it took a while to make the CPU small enough and light enough in terms of power consumption to where it could do all these features and work in a cell phone. So that took time to develop. And at some point, the smartphones were finally, it probably was when they started becoming smartphones. It might be that the first smartphones were modern CPUs, because before smartphones, people referred to them as sometimes feature phones. And those probably weren't a modern operating system. Now, I don't know if, maybe maybe some of the first smartphones weren't a real operating system, or maybe once they were smartphones, maybe they were a real operating system. But there were phones that did a lot, but weren't running they always ran on a CPU, but they weren't necessarily a modern CPU with a user mode and a kernel mode and interrupts and the ability to run a real operating system. Okay, so the things we need to understand are, process control blocks are important. Oh, now let's look in the textbook. I mentioned the textbook gives you I'm sorry. in this chapter on process, here's a sketch of the process control block data structure. Okay, now here's the register data structure. So the process control block is, if the process control block, I've been emphasizing the fact that the process control block needs all these registers. Actually, the process control block's more than just these registers. Okay, so the process control block are the registers and some other stuff. So here's a data structure that holds all the registers. Those, if you recognize them, are the names of the main registers in an Intel CPU. That's the instruction pointer, that's the stack pointer, that's called the base pointer. I forget what these other ones are. Okay. So these are the registers in a CPU. But that was a few years ago. That's not the current, but that's so. But the idea was that these registers would need to be stored in the process control block. So he has this. Notice he calls it the context struct. Okay, so these are the registers. Then the proc struct. So he's using proc to mean the process control block. Okay, it's got a bunch of stuff in it. And there's the context struct, and he calls it context. So this field in that strut is a copy of that strut. Notice you have to read, it's important to learn how to read C. Strut context is the type. It's saying, oh, I want a copy of one of these in this strut, but I'm going to call that field context. Okay. Now, notice that this structure is a pointer to something. It's a int, a pointer to something, an enum, an int, which is the process ID, then another strut, then a pointer to void, which points at something, an int, and then 1, 2, 3, 4 more struts. Okay. A file strut. Okay. This thing keeps track of what files your program has open. If your program is reading data off the hard drive, part of your process control block is which files you have open. This strut here is got to do with your process has a notion of what directory it's running in. Every process is launched from a certain directory. That's called the current directory. Okay, so there's a pointer to a strut that keeps track of what the current directory is. Okay, then there's the context. That's the important. That's what we've been emphasizing. There's the registers are stored in the process control block. The process control block is more than just these registers, but there's the registers in the process control block, and the registers are these. And oh, notice that each register is just an int, because an int is here. This would be, each one of these registers is 64 bits. Each one of these registers in a modern CPU would be 64 bits. That's an int. Okay, so each register value is just an int. Okay, the last thing here, don't know what it even is. Trap frame for the current interrupt. I don't know what that is. I don't know why he put that in there. Okay, I think it has something to do with the hardware. Okay, so I don't know what that one is. Okay, so process control block, the key idea from our point of view is the registers. Because when you want to freeze the CPU in this process, you freeze the CPU by saying, take all his registers, store them in the process control block. That's essentially what you mean by freezing the CPU. So then you can unfreeze the CPU in this process by taking its register values from this process control block, loading them into the CPU. That unfreezes this guy. Real important, the program counter is part of the process control block. Oh, I call it the PC. Intel actually calls it the IP, instruction pointer. So program counter is a common phrase. Instruction pointer is a synonymous phrase. So Intel actually likes the term instruction pointer. So it's the register that points at the current instruction you're executing. Historically, people have usually referred to it as the program counter. It counts where you are, what instruction you're at. Actually, instruction pointer is a better name for it. I'm used to the phrase program counter, but instruction pointer is actually a nice, because it reminds you it is a pointer. A pointer is a memory address. Anything that is a memory address is a pointer. So this is the thing that points at the current instruction. So IP is actually a really good name for it. It's a well-chosen name for it, but a lot of textbooks, and I have the habit of still calling it the program counter, and a lot of textbooks still refer to it generically as the program counter, but Intel chose to call it the instruction pointer, and that's a good name. That's a good name for it. Okay, stack pointer, instruction pointer. See these ones with a P: instruction pointer, stack pointer, base point. Well, no, down here, base pointer. That's the base. BX, actually, I don't remember what that one is. I thought that's not the base pointer. The base pointer is BP. So I don't remember what BX is. I don't remember what well, I think this is just a generic register. I think BCD, that's just BCD, 3 letters in a row. I think these are just the general purpose registers. The BCD are the general purpose registers. See these ones that have an I at the end? Those are called index registers. So that's an index register, and that's another index register. Okay. So, I mean, if you learn the Intel architecture, you learn what the use of each of these registers are. I think the BCD are the general purpose registers. So they can be, they're the ones that you would put numbers in if you want to add them and increment them and subtract them. So those are, I believe those 3 are the general purpose ones. And instruction pointer, stack pointer, BCD, general purpose, couple index registers. I don't remember what the S and the D stand for, and then what's called the base pointer. Okay. All right. All right. So that's our mechanism. Okay. That's our mechanism that lets us create the abstraction of a process. Okay. Now, trying to remember if there's any, I think that's pretty much, oh, I know. Here's another idea that's important. We've been talking about what's called context switch. The context switch means going from this process to that process. You're changing the context. See, even here, the context is the registers of the CPU. So we are switching from one context that belongs to one process to another context that belongs to another process. Or another way of saying we're switching from running this process to running that process. That's called a context switch. Part of a context switch is what's called a mode switch. Now, so the book talks a lot about mode switches. Mode switches only when you switch the CPU from user mode to kernel mode. Okay. Mode switch and context switch are not the same thing. Okay. You need a mode switch to do a context switch, but quite often there are going to be mode switches that don't lead to context switches. Okay, so let me add something to this picture to show you what I mean by that. Okay. Besides this timer here, your computer can have a network interface card. Okay, so let me draw a little box here. Well, I shouldn't put that in red. Let me put it in black. Okay, there's a box down here that's the network card. Okay, so it's referred to as the NIC, the network interface card. The network interface. Okay, the NIC. Okay, the NIC has an interrupt that feeds into the CPU. So there's a NIC interrupt that feeds into the CPU. Okay, so this is the NIC's interrupt. Okay, that interrupt fires when you have some information comes into this would be this could essentially be your wireless device, or it could be if you're plugged into an Ethernet port. But this would be this interrupt says that there's some information coming in on the network. Okay, so if I look in Task Manager, one of the things I can look at in Task Manager is I can say what's coming in off on my Ethernet connection. Okay, see, my Ethernet connection is the NIC. Now, I could be using, I'm actually hooked up to an Ethernet, not a wireless device. But this information coming in on my network is coming in through this NIC. So this NIC connects to my network, and the NIC connects to the okay. When information comes in here, it has to be processed. But that's not necessarily what this program is doing. Like this might be, I'm running Word, Notepad. Suppose this is Notepad. Well, Notepad's not communicating over the network at all, but maybe some information comes in off of the network. That's got nothing to do with Notepad, but the CPU has to process this information. So how does that get done? Well, the operating system is what's responsible for getting this information and processing it. So here's what's going to happen. This interrupt comes in, just like the timer interrupt. When this interrupt comes in and says, there's some extra information on that just came in off of the network. It's the interrupt changes the mode bit from user mode to kernel mode. It puts a specific address in the program counter. That's a different address than the timer would. It puts a specific address in the program counter and jumps you into the operating system in the device driver for the NIC. Okay. Then you start running code over here. Now this is a mode switch because you're going to switch from kernel mode to, you're going to switch from user mode running Notepad to kernel mode running the operating system. But then the operating system is simply going to do some code that gets the data off of the NIC and stores it somewhere in the operating system. So the operating system communicates with the NIC, gets what it needs to from the NIC, and then it returns from the interrupt, which then puts you back over here. And there's no context switch. Because you didn't switch from this process to any other process, the interrupt just said, it's time for the operating system to do some bookkeeping. It's got to get some data off the NIC, store it somewhere in the operating system, and then return to the program that was running. So there's a mode switch. You switch from user mode to kernel mode. Some people do think of this as a context switch. You switch from this process to the operating system context, but we're not going to call that a context switch. For us, the context switch is you switch from one process to another process. So this will be a mode switch. You switch from user mode to kernel mode. Kernel mode means you're in the operating system. The operating system talks to the NIC, finds out what the NIC wanted done, maybe copies some data from the NIC into the operating system, maybe issues some commands to the NIC telling it to do something, and then the kernel just returns to this process here. There's no context switch. There's no need to update this process control block. Okay? The kernel just, you switched into the kernel did some work, and you switch back out to the process. That's a mode switch without a context switch. And that the network interface card isn't the only one that does that. That could be the GPU, it could be the hard drive. Any hardware device will do this. Even your mouse. Every time I move this mouse, the CPU is being interrupted. Okay, the CPU gets an interrupt every time I move this mouse. If you can even see that somewhere in Task Manager, I forget where it is. I don't remember now where it is. Somewhere in Task Manager, there's information about interrupts. I don't remember where it is. But you can actually see that if I move my mouse a lot like this, oh, actually, you probably can't see it in Zoom. But if you move your mouse around a lot, you're actually generating a whole bunch of mouse interrupts because the computer has to keep track of where the mouse is. So moving the mouse, do you see the Zoom is very selective about what it shows you. Like right now, I'm moving this see this picture? I'm dragging it around. It's moving constantly right now. I bet you don't see that. Let me know. Do you see the window moving?
We don't see the window moving.
Yes or no? Do you see the window moving?
No.
No, right. See, Now, what happened is Zoom is real selective about what it shows you. It does not show you that window moving. Does anybody know why it doesn't show you the window moving? Why would Zoom not want to show you that window? Right now, I'm moving it around real fast. And then, like, probably what you see is, you see the window over here, and now you see it over here. And now you see it down here. Probably it just jumps. That's what I'm guessing. You
Yep,
just see
it
it
is.
jump. Why isn't
It's
you,
jump.
why doesn't it show you what I'm doing? Tony said bandwidth. What do you mean? Somebody wrote bandwidth. What? That's actually the right idea. What do they mean by bandwidth? Yeah, bit rate. To show you this level of detail, they just have to send too much information over the network. So what they basically just say is, forget it. We'll leave the window in place, pretend it's not moving, and we're not going to show all this information. We're not going to transmit all this information it takes. It just takes way more bits, more data to let you know that this thing's moving around. Okay? So Zoom is real selective. Okay, but when I do that, I'm generating tons of interrupts. If you grab a window and just start shaking it all over your desktop, you're generating a bunch of interrupts. And there's some place in Task Manager where you can see the interrupts happening. You can actually see that there's lots of interrupts happening. Okay. All right. And if you're downloading something over the internet, like if you start a large download of the internet, you'll be generating lots of interrupts from your network interface card, because if you're downloading lots of data, a lot of data coming in on your network card will generate lots of interrupts, because the data comes in through an interrupt. Okay. All right. So the interrupts can cause mode switches without context switches. For us, a context switch is switching from one process to the other. A context switch means that you take the state of the CPU, put it in a process control block, pick another process, pick its process control block, put its state in the CPU. Okay? A mode switch causes you to jump from wherever you are into the kernel. You switch from user mode to kernel mode, which causes you to switch from when an interrupt comes in, you switch from user mode to kernel mode. When an interrupt comes in, a specific value gets put into the program counter, which directs you into the operating system. Every interrupt has its own interrupt vector. So that's how the operating system knows what it's supposed to do. If this interrupt comes in, one value is put into the program counter, which sends you to one chunk of code in the operating system. That's the timer interrupt device driver. If this interrupt occurs, a different value is put into the program counter that sends you to a different chunk of code in the operating system. That would be the NIC's device driver. If the hard drive interrupt comes in, that puts a different value in the program counter, so that jumps you to a different place in operating system, which is the device driver for the disk drive. Okay, so each interrupt has its own interrupt vector, which directs the program counter to a different place in the operating system. So the operating system, essentially, the interrupts are like function calls. The interrupt is a weird kind of function call. And that's how people think of it abstractly. The interrupt is calling a function in the operating system, which we sometimes refer to as a device driver. The interrupt directs the program counter to a specific chunk of code in the operating system, the device driver for the timer. That interrupt directs the program counter to a chunk of code in the operating system. This is the device driver for the NIC. That's like a fancy kind of function call. Okay, so and then the operating system returns from these function calls, but it returns to your process. Okay, these are what we call asynchronous function calls, because it's not your process that's deciding what function call to call. When your process is running, this interrupt happens. that creates an asynchronous function call. Your program doesn't even know about it, directs you into the operating system. When the operating system returns from the interrupt, it's actually returning to your process, whatever process was running at that time. Now, if it's the timer interrupt, then the operating system chooses to do a context switch. Okay, so the timer interrupt can cause a context switch, but the network interface interrupt is probably not going to cause a context switch. The network interface card, its interrupt just says, oh, it's, the operating system handles the interrupt and then it returns to whatever it was doing. So this interrupt is not likely to lead to a context switch. Now, later on, we'll learn that that's not quite true. We'll learn that this interrupt, which causes a context switch, might lead to a process, the interrupt which leads to a mode switch might lead to a context switch. That's when we do the scheduling, we'll talk about that. Any interrupt potentially could lead to a context switch, but that's got to do with the scheduling issues. Right now, our way of thinking is that this interrupt causes context switches. These other interrupts cause mode switches only and don't yet cause context switches. So when this interrupt interrupts the CPU, the operating system handles the interrupt and the operating system returns to whatever it was doing. So you go back to the process that was running. No context switch. Okay. The context switches are when this interrupt causes this mode switch, which jumps you into what we're calling like yield. Then we cause a mode switch, a context switch from one process control block to another process. Okay, so mode switches are not context switches, and context switches aren't mode switches. The way to think about it is every context switch requires a mode switch, but a mode switch need not lead to a context switch. Okay, so a context switch must be context switch must have there must be a mode switch before there can be a context switch, but a mode switch doesn't have to lead to a context switch. It may or may not lead to a context switch. Okay, so keep that in mind. Mode switches and a lot of times students get these two mixed up. Mode switch means you switch from user mode to kernel mode or kernel mode to user mode. Context switch means you decide to stop running one process and start running another process. A context switch requires loading a new process control block into the CPU to switch from one process to another. So a mode switch is a context switch is a lot more than a mode switch. Okay, all right. Okay, so we've run out of time. So I think we've described everything. I think we've described pretty much everything that's in these two chapters. The abstraction of a process and the mechanism. Where was it? I'm sorry. The abstraction of a process and the mechanism for creating the process. Okay. So I think we've covered everything in here. Notice that he mentions that the hardware is involved in this. So he talks about the sequence. This stuff here, he's really just in words describing what we've been describing here in a picture. Okay, so essentially this picture is, I think, trying to give you a visual representation of what these words are doing in sequence. You think of this as a sequence of things happening. Okay, the hardware does some things, and the program does some things, and the kernel does some things. And you're supposed to think of this as sort of a sequence of steps. So you need to merge this table with this picture. Okay, so think of it that way. When you read this, think of it in terms of this picture and see if you can merge them together. And if you have questions, we can, that's something we could do. If you have a question like, how does something in this table relate to something in this picture? We've been describing it strictly from the point of view of this picture. The book uses the words. He doesn't have any pictures in this chapter other than this one picture that describes in this chapter there's no picture. The only picture he has is in this other chapter, this idea of that the program exists on the hard drive and the process is the program copied into memory. So this picture here is this part of the picture here. Programs get copied into memory. So that's the only picture he drew. He didn't draw any pictures for the mechanism. The mechanism, he never drew a picture. Okay, so here is the picture I think that illuminates all the words of his description over here. But if you have any question, if there's anything in here that that you don't seem to think, if you have trouble figuring out how anything in here connects to this picture, please ask. Because that's what you have to do. You have to make sure that you understand. I've explained it one way using a picture. He's explained it using words and a table. If you don't see the connection, please ask. That can be like, we'll start there. We'll start with that next week. If there's any question about how to connect this picture with this words, please ask on Monday. Otherwise, we'll start talking about the scheduling. We'll start talking about the next chapter. Okay, so make sure that this picture makes sense to you in terms of all these words over here. Okay, timer interrupt. See, timer interrupt. See, timer interrupt. He talks about it in words. Here I said, oh, the timer interrupts something that feeds into the CPU. And it affects the mode bit in the CPU. So I tried to make it in terms of a picture that you can think of concretely. And he's just put it in words. Okay, so he talks about the timer interrupt. All right, so we'll quit there. And make sure that you can make the connection between the picture and the description in the book. Anybody got any last second question? Oh, somebody wrote a question. How does a YouTube video look like over Zoom? I have no idea. I've never experimented with that. I don't know. If I were to show a video while I'm doing Zoom, I don't know what would happen. Because Zoom's real selective. That's like, probably it would figure out that it should show you like if I showed a video here, that's a lot of data. I don't know if Zoom could do it. Yeah, that's a good question. I haven't even tried doing that. Maybe I might have to do something in the Zoom interface to tell Zoom I want to show a video, because Zoom really does try to limit the amount of information it sends over. So like, it doesn't show you when I'm dragging this window like crazy. You don't see this thing dragging around. You just see it also when I stop moving it. So yeah, video would be a good question. Would I need to tell Zoom I want to show a video, or is it somehow smart enough to figure out that it should show a video when it shouldn't show this stuff dragging around? Anybody any question? Okay, we'll quit there. And on Monday, if there's any question about connecting the stuff here with the picture here, please, be ready to ask about questions like that on Monday. Okay, so I'm gonna click on stop sharing. Have a nice weekend and see you on Monday. Bye.